Welcome everyone to today's Explainer. I am absolutely thrilled to have you here. Think of today's session as a keynote presentation coming straight from the absolute cutting edge of deep tech. We're going to dive into a monumental leap forward in material science. Space Seed Holdings, teaming up with Professor Yoshihisa Mori's research group at Okayama University of Science, just announced something massive. They've developed an ultra-high-pressure spark plasma sintering system. And guys, this doesn't just tweak how we make materials, it literally rewrites the rulebook. Whether you're a materials scientist yourself or you're just fascinated by the idea of humans actually living in space, you're going to want to pay close attention to the data we're presenting today.
Here's our roadmap for today. First, we'll look at the high-pressure challenge. Then, we'll introduce a new multi-anvil methodology. After that, we'll dive into the experimental results and validation. And finally, we'll explore building the future in space.
Okay, let's dive into this. To really frame our discussion today, I want you to consider this philosophy from Kengo Suzuki, the CEO of Space Seed Holdings. He says, "Pressure is a pen of a blueprint that rewrites the state of the material itself." You know, we usually just think of pressure as this crude, crushing force, right? Something you just use to smash or solidify a powder. But what if we treat pressure as a highly precise design variable? It's a tool that lets us fundamentally alter a material's state, essentially rewriting its genetic code, without needing those extreme energy-heavy temperatures. And that is exactly the philosophy driving this whole research. So, part 1, the high-pressure challenge, sub-millimeter limitations. Traditionally, researchers have relied on a piston cylinder type of high-pressure cell, basically applying force along a single axis. But here's the thing. This paradigm has a fatal flaw. When you push to extreme pressure limits, your sample size is restricted to a tiny sub-millimeter scale. Plus, the internal conditions get incredibly uneven. So the core scientific problem was basically this. The higher the pressure you use to change the material, the harder it becomes to accurately measure what's actually happening inside that chamber. Now, looking at the ideal goal on the right, what we really need are larger millimeter-scale samples under uniform isotropic pressure. That's the baseline the industry desperately needed to hit to get precise, quantifiable evaluations.
Moving on to part 2, a new multi-anvil methodology, the palm cubic solution. Let's see what Professor Mori and his team actually built.
To establish our foundation here, we need to quickly define SPS, or spark plasma sintering. This is a technique where pulsed direct current is applied to pressurized powder. This allows the material to rapidly sinter and densify at way lower temperatures than your traditional baking methods. Now, standard commercial SPS machines, they might reach tens, maybe hundreds of megapascals. But to actually rewrite a material's blueprint, this research group was determined to push way past megapascals and go deep into the gigapascal range. So how do you generate that kind of extreme force? Well, the team developed a totally new clamp-type high-pressure generator based on a palm cubic structure. Instead of just pushing from the top and bottom like a standard piston, they use 6 anvils to apply pressure isotropically. That means equally from all sides. And this brilliantly illustrates the physics here. By installing this multi-anvil clamp directly inside the SPS chamber, they totally bypass the limitations of single-axis compression. The result? They successfully generated stable pressure exceeding a massive 10 gigapascals. But as you know, extreme pressure is only half the equation, right? Controlled heat is just as vital. By integrating this completely new thermal insulation layer, the team actually managed to apply roughly 100 amps of current to heat the sample up to 1,273 Kelvin. What's truly remarkable here is the localization. Even under that extreme current, the heat stays completely localized to the sample itself. The surrounding anvils and the main body, they remain totally protected from the temperature spike. This proves their insulation design is highly effective and completely stable for ultra-high pressure experimentation.
Section 3, experimental results and validation. The data speaks. Let's look at the hard evidence. To actually prove they were generating precise, uniform pressure, the system obviously needed rigorous calibration. The researchers tracked the electrical resistance changes, specifically the phase transitions of bismuth, using them as fixed pressure points. As you can see, applying 50 newton-meters of clamp torque successfully triggered the bismuth 1 to 2 phase transition, which firmly estimates the pressure at about 2.55 gigapascals. Then, pushing it to 100 newton-meters hit the 2 to 3 transition at 2.70 gigapascals. This empirical evidence absolutely proves the system is generating highly quantifiable, controllable pressure.
So the crucial point is this retrieved sample size of 2 millimeters by 1 millimeter. Now, I know 2 millimeters sounds completely tiny in everyday life, but recall our scientific baseline. Traditional ultra-high pressure tests were completely trapped in the sub-millimeter scale. So retrieving a fully formed, uniform sample at the millimeter scale, that is an absolutely massive leap forward for material science. It means we can finally properly evaluate the materials that we synthesize under these extreme conditions. To really demonstrate what the system can do, they took standard silicon dioxide, just raw SiO2 powder, and placed it into their new system. They applied 75 newton meters of torque, heated it to just 873 Kelvin, and successfully transformed that raw powder into transparent glass. By using immense, evenly distributed pressure, they radically lowered the temperature needed to turn powder into clear glass. This completely validates their initial philosophy. Pressure is, without a doubt, a powerful design factor that can literally rewrite the state of a material. Which brings us to part 4, building the future in space, the 2040 vision. The applications this technology unlocks go way beyond just making glass. With this platform, we can synthesize entirely novel materials at much lower temperatures than we ever thought possible. We can control unique non-equilibrium states of matter. We can even better explore the creation of high-value, high-pressure materials like synthetic diamonds and cubic boron nitride. But the ultimate application, the real paradigm shift for space seed holdings, is in situ resource utilization for space exploration. Basically, using the raw materials we find off-world instead of having to launch every single thing from Earth. Let's put this into a timeline. Space Seed Holdings was just established in 2024. Here we are in 2026, and they're already announcing this ultra-high-pressure SPS system. Their long-term goal? Human habitation in space by 2040. Now, the physical reality of space travel is that cargo weight is incredibly restricted. We literally cannot afford to pack up huge factories and vast quantities of building materials from Earth. It's just not feasible. If humanity is actually going to live on the Moon or Mars, we have to take the dust and rock that's already there and turn it into usable structural materials. And we have to do it using very low energy. This SPS technology, using extreme pressure to force materials into new states at low temperatures, is the exact foundational check we need to make that 2040 vision a reality. Which leaves us with this final thought. If we can rewrite the blueprint of materials today, right here in the lab, how will localized high-pressure synthesis turn sci-fi into nonfiction for space living by 2040? We are officially moving past the trial-and-error phase of material design, and we're entering an era where we actively engineer the building blocks of our off-world future. Thank you so much for joining me today to explore the science that is shaping our next frontier.